Good morning, everyone. Just going to start going over my project now for London and B-Sides. This is going to be expanded on before I get to B-Sides into egg hunters and stuff. But this is what I have put together for B-Sides Ottawa just to trial it out and see how it feels. So let's just jump right into it. So reverse engineering for bugs with me. So that's the name of the class for today. Okay, so what we will learn we're going to cover static analysis of a vulnerable server using IDA Pro, and we're also going to do a dynamic analysis of the vulnerable server using WinDBG. So we learn how to walk a binary with two of these, and it all makes sense once we get into it. We're going to cover some basic 8632-bit assembly, which is key to doing anything with this stuff. We're also going to be creating Python exploit scripts. So I'll show you just what those look like. You won't be an expert walking out or nothing, but it'll give you a good idea just how we go about our exploit development process. We're going to do some basic shell coding, bad character analysis. So seeing what characters we can't use. I think we all know about 00 null terminator. We can't use that, of course. And if you look up right here, this is a null terminator right here. So we wouldn't be able to use this address right here. And we will cover also some basic Windows internals. Okay, so learning outcome, what I want you guys to walk away with is having a basic understanding of some tools used in reverse engineering, understanding the importance of assembly programming, very important. Grasp how Windows syscalls are loaded into memory and how we can use these. And I'll be stepping from call to call so I can show you how these are all set up on the stack and what information we can glean out of those. Also, understanding how bad characters can affect our exploit, and we'll get into that a bit. I just explained the null terminators. There's carriage return and stuff like that we'll get into. How we can use egg hunters. We're not going to get into egg hunters on this one, but by the time I get to London, we'll have the egg hunters worked into this class. Basics of a buffer overflow. We're going to do a buffer overflow and get remote code execution here. And understanding gadgets and how to find them is also an important topic. Okay, so like what we're looking for. We're looking for calls to known unsafe library functions or important functions, such as stir copies, sprintf, scanf, gets, memcopy, where the size parameter may be derived from the input. So if I'm controlling the input and that input doesn't get any bounds checking like these do, it can overflow the return address, and then once we overflow the return address on the stack, we can control where the computer is pointing and what it does next. Okay, so Sam, well, so malloc and alloc with size computed from input, followed by memcopy remove SB, where the size is unvalidated user input. So basically, if the stack is a container and if we overflow that container, the program's going to try to crash. It's going to return to the EIP to return address, which we now control. Then we can make the EIP go where we want, the index pointer, and then we control the flow of the program. So when we get our server or whatever we're going to work on, it's most. I just had a break in at my house a couple of months ago. The first thing the crook is going to do is go around and check the doors. If the doors are open, they get in. Reverse engineering is much the same. We have to find a way into the program. And we got to, if we can find the easiest way in, that's what we're going to do. So, what are ways into servers and stuff? Well, we're going to go in through the ports, right? So, what we can do, we can use programs like free programs like TCP View, which has an external if it has an external IP, we can get remote code execution. And if it's just a local address, we can get privilege escalation. We also use services.msc, and if the program is running as a Windows service, we can check for insecure permissions there. Our server today is not a Windows service, but I'll show you what we look for there. Okay, so let's get our 32-bit fire it up here. And here's our vulnerable server. So let's have a look with TCP view. And here's vuln server. So it's listening. Let's do options resolve address. And it's listening on port 9999. Now, that's the only port we have into this one. So when you get some servers, you'll have all kinds of services running on different ports and that, and they're all different avenues you can explore to get inside. So now that we know we only have one port, there's only one door to get into this break and entry. So, okay, that's fine. I'll show you services.msc because if it is a Windows service, this really does come in handy. And over here you can see we go down to V and it's not there because our server isn't a Windows service, but some servers will be. And you can see here we got local system and local service. So let me just haul up what we were looking for. So these are basically the permissions of the program. And if it's running at a high system like local system, we can get full control of this. If not, we can get like maybe a user shell onto the system. So let's read this. Local system NT authority system. This is the most powerful built-in account on a Windows machine. According to Microsoft, the system account has extensive privileges on the local system. This is our root. So locally, it effectively has full control, similar to administrator or beyond. Implication is if you run a service on your local system, a compromise of that service can give you broad access both locally and remote, depending on what machine account has. It's very high privilege, treat carefully. It is also the most privileged account you can possibly use, more privileges than administrator. So if it's running this, we can get full administrative privileges. Okay, let's move on to the next one. Now, this is the other one we've seen, and this one's called local service. This is a much more restricted account, and Microsoft says the local service account has minimum privileges on the local computer and presents anonymous credentials to the network. Locally, it has very limited permissions, something like a standard user, okay? So basically, we're looking at root and user when we're looking at two of these. Implication, good for services that only need local access and do not need to access network resources. Running as a local service reduces the risk of compromising major privileges on the network. When you use it, when your service only needs to act locally, file access, etc., and doesn't need to authenticate to other machines. So that's the reason you would use it. And when you're doing your break and entry off the start here, these are things you have to look at. So the only thing we've gained so far is we know our port. We don't know the permissions in that because it's not running as a service. So we'll shut that down. Okay, so we have our server up and running here. Next, I'm going to fire up Netcat. Local service and our port that we just found in the last stage. So let's have a look here. Or local host. Jesus, what am I doing? I'm an idiot. Okay, local host. I wonder if the capital. Oh, okay, here we go. So, welcome to the vulnerable server. Enter help for help. Okay, so I'll enter help. Unknown command. Okay, let's try help. And here it is. Okay, so I'm going to do Troon A. What happens? Troon complete. Okay, so we can go down through all of these. They all do basically the same thing here. We put in an input with the Troon or the GDOG or Gmon, and then it comes back complete. So now what I'll do is we have this up and running. We have our local host set up in 9999. So now I need to start sending my Python scripts to this to this vulnerable server. So we'll come over to our Kali machine, and I already have these exploits done up. So if we just have a look here, we can see basically all I'm going to do is send a byte array of 41s, which is A's times 100 to this server. So let's start off with that. This is our first step here. And let's open a terminal in our folder. So let's do Python 3 and let's have a look at that one troon dot py, and then I'm going to put in the packet sent. Okay, so let's go and I jumped the gun there a bit. So let's okay, so let's set up our server here again. Vuln server. Run as the administrator. You always have to run as the administrator. And let's attach to our vulnerable server right here. Okay, so the first thing I'm going to do is I need to hook the receive function. So let me just haul up my slide on the hook. So hooking the receive function is what we're going to do next. Now that we have our way in, we have port 9999. I have an exploit done up to send a whole buffer of A's to the server, and we're hoping it might crash or overflow, and then we can go from there and start exploiting it. Now, with fuzzing, we will send a whole bunch of information at it. It's not necessarily the best way to do it, but fuzzing is really quick. Whereas reverse engineering takes time, but you might find some really great stuff in there that you would not get with fuzzing. And I'll give you a little heads up. That's what we're going to find out today. So hooking the receive function to track our exploit as it arrives at our vulnerable server, we must hook the receive function within WinDGB. That's what we're going to do next. This is where Windows system internals become super important. The receive function works like this. So we have the socket, the buffer, and the size, and the flags. So we pay attention to the buffer because this is where our information is going to be copied into, and we're hoping to overflow this buffer to cause an overwrite of the EIP and the return address, and then take over control of the flow and pwn the server. So we pay attention to the buffer and the length, which tells us how much is going to get copied into our buffer as well. Within WinDBG, we just use our breakpoint for win receive. So this is what the function looks like here, okay? So our buffer is important, our length is important. Usually it doesn't have flags, and the socket's not really important to us too much, but when we get to a call for the receive function, I'll be able to dump all this and we can have a look at how it's lined up in assembly to do these Windows syscalls. And okay. So let's set our breakpoint. Let's set our breakpoint in our WinDGB here, and we'll hit G for go. So now this debugger is hooked up to the vulnerable server. And if anything comes in and hits the receive function, we're going to hit our breakpoint and then we'll know right away. So let's go over and let's send our packet again here. Packet sent. We come over here and we can see something did get hit here. So I'm going to look at 5. Oops. Yes, ESPL5. Here we go. So here we are at the receive function, and let me just haul up the receive again. Let me just haul this off to the side here. So here's the receive. Here is the socket. Here is the buffer that it's going to be copied into. The initial length is going to be 1,000, and we have no flags. So let's just have a look here. Control C, and let's have a look inside that buffer. As you can see right now, the buffer is fully cleared out. There's nothing in that buffer. So let me do a couple more steps here. And these next couple steps, we really don't have to pay too much attention to. As you can see, it's just receiving the input. So let's keep stepping over until we get back inside our server. Okay, so here we are. So now if we do a DD on that, you can see nothing got copied in. So this is a problem. So there's something happening that is not allowing us to copy our input in. So let's open up our IDA Pro and open up new. Now with 32-bit, you have to go way back and use whoops. Okay, there's a problem there. Let me just permission denied. It's not going to let me. Okay, so let's try this again. New, open, overwrite. Oh, we're going to call it something different. Bone server 1, 2. Okay, so now let's import everything. Now, when we open up our IDA Pro, now this is going to be for the static analysis. So the difference between static analysis and um, dynamic is dynamic, we're looking at everything. Here we're looking at EAX register, the stack pointer, the EIP. We have everything that's happening step by step. Now, when we get into here, we're just basically looking at where it is. The nice thing about it, we can look forward and backwards much easier to see what the input's doing in our IDA Pro um, compared to the dynamic analysis in WinDGB. So both of them together give us a lot of good options. So um, what we will do is we will have a look for our Troon. And now this was the input we were going to start with. So what I'm noticing is right here, we're doing a string compare and it's looking for this Troon. Now, if it doesn't, it just keeps moving on and moving on and moving on down these if else statements. So these are all gates, logic gates, really. So the program is basically checking for these words to be in front before it actually copies it in. So why our buffer didn't get copied in, that's the answer right here. So the next thing I need to do is add Troon to my exploit. So let's go back over to our Kali machine. And let's have a look at our exploits. So all it did was send A's. That did not work for us. So once we had a look at our input, we realized that the Troon part was really important. Um, so what you'll find in a lot of these servers and stuff, they'll have different opcodes and different restrictions, and they use compare statements to make sure those have it in it. As you can see, we didn't have Troon put in. So right now I have Troon, Trun, and I have our A's times 5,000. So I'm going to try to overflow that buffer. So let's go back to our 32-bit here. And we'll shut down our WinDGB. Open up our vulnerable server again. Now let's attach our WinDGB. we will set our breakpoint on the receive function again. And we will hit go. So the server is listening, or WinDGB is listening for our input. So let me open a terminal here. So our next exploit we got called toTrune.py. And again, I'll open this up. So it's sending the trune command with the A's, much like we did with our netcat. But I can jump right to the last exploit in this and pwn it, but I wanted to show you the full process as we go through. So mistakes and all, we'll leave them. I left them in. So let's do trune. Trune2.py. Are we in the right? On free trune2.py. toTrune, that's right. Here we go. So as you can see, we hit our receive function. So now this is right before the receive call gets called. So what happens is the stack pointer has all the variables lined up to do this call. And we go back and we see our socket right here. We see our buffer that it's going to get copied into. And then we have our size and our flags right there. So let's do, and as you can see, there's nothing in that buffer. So I'm going to continue on here. We'll step through a few of these socket calls and stuff. And let's have a look again. And boom. Okay, so now we got in. So as you can see right here, this is trune, backwards, Trun. And we have our buffer of 41. So this is a good start. Now we managed to get inside that buffer. So now what we're going to do is walk the program. So basically what we got to do is open up our IDA Pro, come over to Options, General. We turn line prefixes on, and then you can notice that the addresses are right here along the side. So let me just minimize this a bit. Here we go. Let me haul this over. Close that one. Okay, so right now we are at 401,984. So there's our 401s. And as you can see, we have a graph view here. So what I'm going to do, so 401,981, 984. So we are at this string compare right here. So the first thing we're hitting is an FL statement. And that's what FL statements look like in assembly. So basically it's saying, is help in the command? Is it 5? Okay, so now it's looking for help with a space after it. So I'm getting a little weary now because maybe I didn't notice that in my first pass through where I didn't walk the program. So I'm noticing that there's a spot here. If we go back and look at my exploit, I don't have either spot there afterwards. So now when it checks for that stuff, it's probably not going to go in. So let's keep walking our program. And what we do to walk it is we just hit PC, which brings us to the next call. Proceed to the next call. So 4019EC. So let's go 4019EC. So as you can see, this is the help. So let's skip to the next one. And this is called walking the program. So 401A61. Let's have a look here. A61. So it's doing another string compare and it's looking for stats with a space after that is 6 bytes right here. So it's not going to find stats in our comparison because we have true put in. So jump not 0. If the jump is not 0, it's going this way. If it is 0, it's going to go that way. So that would mean that it found stats. So we're at runtime now. And let's see. As you can see, it's just a whole bunch of if-else statements. Does it have this in the beginning? 401 B05, here we are at the next string copy. Okay, so now we see true down here. So 3 more steps through walking our program. We should be getting there. So I'm going to hit PC. So that's BA9 right here. So I'm going to hit 2 more calls to get us down to our call. So that's 401 CD. This is a string compared to see if it's S run. Now we're down to Troon. So now I see my problem. And what's going to happen here is it's going to take this next jump over to Gmon instead of coming over here to malloc and men, which would be allocating the memory and then setting the memory to 0 prior to copying our buffer into it. So with this jump not 0, where I only have 4 bytes of memory or 4 bytes of command opcode at the beginning, and this requires 5, it's not going to take the jump. It's not the same. So our little tiny mistake there, we couldn't pick up until we actually walked the program. So this is the big part about um, doing reverse engineering is this kind of stuff um, you would not get when you're fuzzing because you would just fuzz it and you wouldn't get any of this unless the fuzzer accidentally came up with true with a space at the end. Nothing would happen, right? So this is the importance of this. Um, so here we are at this stir copy here, CF1, C4D. Okay, so we're at this one here. So let's do the next step. And this one's stepping into the Troon, CF1. So here we are at CF1, and it's going to do a string comparison of this versus what we have at the beginning um, of our exploit. So if it doesn't take, it's going to continue on down here, checking more of these commands until it doesn't find anything, and then it's going to come down here and keep going, and then it's just going to error out because it does not find any of our inputs. So let's go back up to, here's GDog. Here's our Troon. So we are, let me confirm. Yeah, so we're at our string copy here. So I'm going to proceed to the next call and see where this takes us. So we're at DFO. So as you can see, it did not see Troon and copy into our buffer. What it did was say Troon is not it, and it moved on to the next one, and it'll move on to the next one, and then it'll just error out at the end, okay? So I want it to take this route, so I'm going to color this in. Okay, so then I want, so that would set the memory. So let's have a look at this one here. This is basically just comparing to make sure the strings are uh, valid to put into the buffer. Nothing big there. So let's go back and we'll send our Troon again. So let's shut down our WinDGB. And let's go back to our Kali. So this exploit was not good. We need a space after that if it's going to follow our Troon down. So The next exploit I make, of course, has our 5, 1, 2, 3, 4, 5, and Troon with a space. We also have a bunch of A's we're going to put onto it, and we're going to see if we can get this copied into our final buffer, which we see Malik and stuff, and I will get into that this run around. I'll explain those to you as well. So 2 Troon didn't work, so now we're on to our third exploit script. So you can see there's a lot of work that happens, and I'm sort of dumbing it down a bit here with pre-made stuff, just for the flow of the class, okay? So that's our new one. So we're going to try Tree Troon. Say that one 5 times fast. So let's get our vulnerable server. Here's our vulnerable server. Okay, so let's do file attached to a process. And there's our vulnerable server. We're going to set our breakpoint. We're going to hook our receive function, like I showed you guys earlier. And we hit go. So the debugger is running and listening. So we come back over to our. So we're going to send Troon this time. And as you can see, our breakpoint has been hit. So we're going to have a look at what's set up on the stack for this call. So here is the buffer, the initial buffer. And as you see, there's nothing in it. So I'm going to step over the next few sock calls. And now we're back into the vulnerable server. So let's have a look at that buffer again. And as you can see, there's our Troon with our space now. So that should be good for our FL statement we hit with Troon. So that all looks good. So I'm going to step 1, 2 ahead here. So I'm going to head off to A61. Let's go. We're going to be up here. So here we are. So what else we can do too is color these, because these are the ones we stepped through. And we stepped through help here as well. And these give you a good good way to, you can't really see too much on the graph view there, but it does help as you go down through. So the next one, of course, is going to be this step here. 0B5. That's that one. So let's, whoops, let's color this one red as well. And we're going to step through this one here. So let's do that. BA9. Okay, so we have 2 more here. We know we're going to step through. And we will confirm it with our debugger here in a second. So here's our Troon again. This is where we went last time. We want to come over here to the Malik memset. So just let me step through 2 of these, and then I'll haul up something to explain to you. So CF1, we should be at the Troon now. Here we go. So we are at the string compare for Troon. So let me just haul up my. Okay, so things we're going to see right here now is Malik. So when you know these functions, you can look at just before the function call, everything will be set up on the stacks identically to the MSDN. So if the same programmers here, you know how important MSDN is. Malik is going to basically assign a memory location for our buffer in the heap, and it's basically on a size basis. This is the size of our buffer. What else we're going to see here is memset. So basically what memset does, it lists the destination, which is going to be our buffer that was just allocated. Int C is the number or integer that's used to fill that space. So usually it's 0, right? And then the size count, like how big that buffer is going to be at that destination. So that's the two calls we have coming up right here. And another one that's been happening that we keep seeing as right here, we can see with the troon here. So the string compare, the first character, string 1, it compares it to string 2, and then if it's 0, which it should be, it goes with the jump. If it's not the same, it goes to another if statement. So let's have a look at where we are here now. So we're at CF1. So we're right here at this comparison. So now, last time it stepped over here, so I'm going to paint this one yellow. Let's just wait. So this was the bad step that it just kept going on and checking the rest because the troon wasn't correct. So I'm hoping the jump is 0 and it jumps over here, right here. So let me just click. Let's step to our next call. So we're at DO5 now. So we are at the malloc. So we did it. We corrected our last mistake. We discovered that this space after the troon was extremely fucking important, and we made it. So we've overcome one problem we've had. So now we can see malloc and memset. So I already showed you what malloc was like. So what I'll do is we'll do DDS ESP length of 5. So it's all I'm doing is saying from the stack pointer, give me what's set on the stack for a length of 5. Because before the call, all these things get pushed onto the stack according to the MSDN. So let's have a look at the call again. So it's malloc. So let's have a look at malloc again. And basically, it's going to be the size. Okay, so here's the size of our buffer. Let's have a look at. Here's the size of our buffer right here. So it's going to be about 3,000, the BB8 right here. That's fine and dandy. So I'm going to move on to the next call. And the next call we hit is going to be the memset. So what the memset does, let's haul that up again. We're going to get the destination here. So this is important because we got to know where our buffer is going to be copied into. And then it's going to zero it out with zeros, and that's the count. So we should see the size of our buffer and the destination of our buffer. So this is where our information is getting copied into. So let me just hit. Oops, fat fingers here this morning. So here is where our buffer's going. And as you've seen in the last one, it's the same, BB8 for our size. So let me do Control C. Let's have a look at this buffer. So as you can see, there's some stuff in it there now. It's not zeroed out because we haven't done this memset yet. So let me just do PC. Now we're at DA1. Okay, so as you can see, something just happened there. We had our debugger running like crazy. DA1. Let's go. Okay, so let's have a look here. Um, Something happened there where we did not get copied into that buffer. Um, let's have a look here at the buffer again. And as you can see, it did not get copied in. Something weird happened, and we done a weird jump there. So that's telling me I'm missing something. And I'm telling you, when you start this off, this is the most frustrating fucking shit you can ever. It makes you feel stupid. It makes you feel not smart enough to do this for a line of work. And the great thing about that is when you figure it out, you feel like a goddess, right? Or a god. Your choice. So, what I came to here is there's a comparison here, um, and it's looking for 2EH. So it's looking through our input for 2EH. What's 2EH? I overlooked this when I was doing the initial one. So I left leaving it and the mistake in just to show you the full process of hauling apart a server. So it's looking for a period. That's what it's looking for. And if I didn't get a period, I get copied into actually, nope, not that one. That's the one we get copied into if we're good. We get copied into this one here, and it just basically turns into an error and crashes the program. Um, so that's not good. So we got another bit of information from walking the program again. Why is Kelly logged out? Okay. So onwards, upwards. We're not even halfway through our exploit process yet. So, so let's go back to our Python scripts. Python's really important, guys, for this line of work. So, um, if I had any recommendations to start off, it would be start off with Python and assembly, and after that, you're good. So, we have our Troon with our five um, integers. We now have added a period because it fucks it up if it doesn't. and and honestly, like the first time I was going through the program, walking it, you get to that point and you're like, why didn't it take that jump? Well, that's why it didn't take that jump, is that period. So let's get back to work here. Enough sitting around. Let's pwn this bitch. Okay, so run as administrator, attached to a process. There's our own server. We, of course, hook our receive function. And we hit go. So now, we're all set up. So let's go back and we're sending Fortune this time. And Fortune is set. Okay, so we hit the receive function. So we're going to have a look at our stack pointer and see what's set up for the call. Um, so there's our socket up here, and there's our buffer, and there's the length of it. So let's have a look at that buffer. And it's nice and cleared out. So hit PC, step through these few sock calls. And here we are. We're inside the server. So here we go. Now we can start seeing our Troon with the space, and now the 2E, that's our period that was messing everything up. And there's our buffer. Okay, so that's perfect. Perfect, perfect. So let me step ahead here. And let's go back to work. Is this the one I'm working with? Let's go back to work. So probably up here in the help. Let's have a look. 9EC. Yep. So we're here at string compare for that. So we're going to step through. Actually, let's step through too because we already know what's going on there. So we're at BO5. One. So here we are at BO5. So I'm going to step through 3 more and get us down to Troon. So step to the next call, to the next call, to the next call, and we're at CF1. And here's CF1. So we're at the string compare, making sure that it has Troon and the 5. Okay, so let's do our next step. And we're at DO5. We're at the malloc call. Okay, let's step to the mem set. And then we're going to have a look at where our buffer is going. Let's have a look here again at mem set. Here's the destination, and this is what it's going to be, zeros, and then the size count. So here's the destination. It's going to be flooded with zeros, cleared out, and that's the size. So let's have a look. Calculator. Let's do view programmer and hex B8 equals 3,000. So we're moving it into a buffer of 3,000. That's what I thought. So let's have a look at that buffer. And as you can see, there's still some stuff in it. So let's do step to the next call. Have a look again. Still nothing in there. So we're at call D69. Okay, so let's have a look. Okay, so let's do the next call. D77. Okay, so we just did our comparison here for the 2E, and we managed to jump into, finally, into str copy. Okay, so str copy, I do have a slide on this. I hope you guys don't mind my slides. So here's a str copy. So basically, what we're going to see is the destination, string destination, the string source, and the count. Now, we're getting into what's called a buffer overflow. So if you ever heard of remote control execution, this is where remote control execution happens. The problem with str copy, and a lot of these other ones that I mentioned earlier in the class, is they don't do bounds checking. So it will take a large input and it'll put it into a small buffer. That small buffer then gets overflowed and then it overwrites adjacent memory. The adjacent memory is usually the base pointer and then a return address as they sit on the stack. Once we overwrite the return address, we have control of what the computer is pointing to next, and then we can fully take over the computer. Okay, so I'm sure you've ran MSF Venom scripts or MSF console scripts and done this. However, this is the hands-on, doing it yourself way. So we're down here. Let's mark this one red too, because I'm excited because we're actually going to get um, copied into our buffer at this point. So let's have a look at our string compare. And yes, ESBL5. So there we go. It's getting copied from this buffer. Let's haul up our string compare again. Or string copy, sorry. So it's getting copied from the destination source into this source here, and it's 3,000. So destination right here, source right here. Oops, let's hold that up again. and then the count, which is 3000, which is right here. So let's have a look at Control C. Finally, finally. So as you can see, we're copied into our last buffer. Um, so let's have a look and see how much the program has left. And as you can see, we're right to the trim complete. If you remember when way back when we had a look with Netcat, we got trim complete to come up. So this was walking the full program from input to it being trim complete. So I got a funny feeling we're gonna step here next. so so let's hit PC. An access violation. Okay, so when you normally do fuzzing, this is what you're looking for. You throw a whole bunch of crap information at a program, and you hope to find an access violation. So what's happened is you can see these 41s. Okay, so what happened? That is all capital A's from our input, and we overwrote the EIP. Okay, so I got a little diagram here. And this is basically what just happened. So with a normal buffer, you have the stack pointer on the top of the buffer. You have the base pointer at the bottom. And then the return is where the computer goes to when the program is closing. So if it encounters errors, it comes to here. And this is where you see the index pointer. And this is where the index pointer is pointing to when it crashes. So what happens, the stack pointer stays up here. We overwrite the buffer, we overwrite the EBP, and now we overwrite the return. Once we overwrite the return, the program crashes, it's going to point here, and now we have control of the flow of the program. So we can do some badass shit from here. So this is really good. When you see the access violation like that, you can start getting excited. So that's that. Let me have a look. Okay, so that looks good. I hope you guys understand that. So when we come over, and as you can see, we have the base pointer is overwritten with A's, and the EIP is overwritten with A's. This is really good. So now, what I have to start looking at is coming up with a new script. So we did Troon. So now I have our Troon, our space, and our period. Um, so what I'm going to do now is buffer. Okay, so what we would do here is we're going to fill our buffer with our. Let me see if I have it in here. Okay, so what I'm going to do. Top there, and let me just take this out here. So what we got to do now is we got to find the full size of our buffer. So we already looked and we seen that the buffer at the end had 3000 characters or whatever. But what we'll do is use some tools here. So let me just MSF pattern create, and I'm going to create a block of 6,000 characters. So now what we're going to do, we're going to put this into our exploit. And let me just tag that. And oh, we got a mistake right there. Here we go. So now basically what I'm going to do, I'm going to fill this buffer. And if you remembered, we overflowed the EIP, which pointed at the return address. We overflowed that with A's. Now, if I just send a buffer of A's in, I can't really tell what part of my buffer overflowed it. So now I'll send in a cyclic pattern that we can get the offset for in EIP, and then we can find out the exact size of our buffer. So I'm gonna file save as true size dot py. Okay, so now we have that. So let me. Okay, so now we're going to do true size. So I'm going to call this one. Okay, so I'm going to call this one rename true size, and I'm going to call it 4A. Just keep. Sorry, this is a run through for the actual course, so so you guys get to see me put stuff together here too. Okay, so let's fill our buffer. Let's go back to our windows. And I really, if there's anyone out there who's really good with Windows programming, I'll show you the biggest problem. I hate having to click run as administrator there. So if you have a way that I could just always be administrator, that'd be dope. Okay, so let's set our breakpoint on our receive function again. And hit go. Okay, so now we're going to send in our pattern. And it's called 4A true size. Okay. 4A true size.py. Okay, I got that right. Woohoo! And it's hit. So now with this one, I don't need to walk through the program. I've already walked the program completely to the very end and know that my buffer with a true 5 integers and a period is going to get copied into our buffer. We just proved that with our last walking. So what I need to know now is the size of the buffer. So if I just hit go, this program's going to crash just as it did before. But what's in EIP is going to be what we need. So as you can see, EIP is this random character phrase here. So just let me copy that. Let's come back over to our Kali Linux and let's do pattern offset. And let's put our here we go. So our exact match at pattern offset 2006. So that's right up to our return address. So now I have a buffer I need to fill with A's for 2000 bytes. I then need to set up a skeleton now that I'll put B's on my return address, and then I'll put C's after the return address. So what this skeleton does is, let me go back to our photos here. What this skeleton does, we're going to fill the buffer 2005 or 2007, whatever was there. And then here on this return address, I'm going to put B's. Now, when the program crashes, and I'll show you, let's go have a look at the crash here now. You can see the stack pointer is pointing to this right here. This is just below where we are overflowing. So I'm going to put a bunch of C's that would take place for my shell code down here below the return address. At the EIP, the return address, I'm going to put a jump ESP gadget. Now, what does jump ESP gadget do? Once it gets to the EIP, it'll jump to the ESP, and then hopefully ESP will be pointing to some NOPs and our shell code, and then we'll get full shell. Okay, so let's have a look here. How am I doing for time? I don't think I can tell with this one. Okay, so what we will do now, we know the size, we'll shut that down. Open up our vulnerable server. Okay, so let's hook our receive function again, just to make sure we got it, and hit go. Now, let's go back to our scripts. So we just did the size, we got the size. So now, next what we're going to come into is, actually I should have called that one 5A. Okay, so now what we end up, we found out that our buffer was 2006 bytes. So we have our true and we have our dot, we have our 2006 A's that are going to fill up that buffer. And now this is my skeleton. So basically I have these B's set up on EIP. It's 4 bytes. So that's going to be a gadget. So what we'll do, we'll find a jump ESP gadget within a binary, and it'll jump then to these C's right here and execute our shellcode. So I'm going to put in 700, which is way bigger than our shellcode's going to be, but I want to see size, just how much I can fit down there. Okay, so we are up and running here. So now we're going to send our skeleton buffer. Okay, so let me. So this one's called 5 Troon buffer. Okay, and now with this one, I'm not going to walk it. I already know where it's going to go. So now I want to make sure that my EIP has B's in it. So as you can see, the EIP has a whole bunch of B's here. If we do what the ESP is looking at right now, it's pointing towards my 3s. So that's really good. So what we'll do, where these two 42s, the B's are, we're going to put a jump to the ESP gadget. So when the program crashes, it comes back to the return to the EIP. It sees a jump ESP instruction. It jumps to ESP and then it hits our 3s here, which is our NOPs and our shellcode. Badass, right? So that works. Our skeleton's working. Everything's looking good. Awesome. So let me just set our vulnerable server up. Okay. And we'll hook our receive function. And hit go. Okay, so let's go back to our Kali. So our skeleton worked great. So that's there. So that worked great. Our B's were on the EIP where we wanted it. Okay, so let's move on to 6. So now, I talked about bad characters at the beginning. When you're picking gadgets or you're doing any kind of exploitation, you have to make sure that there are no bad characters in either your shell code or your gadgets. So what we do, we flood the buffer with a whole bunch of bad characters, and we go in and we have a look. Now, as you can see, 00 has already been taken off, because we know that one's a bad character. Um, these things can be buffer dependent. Let me just, I do have something here on that. Okay, so what we're going to be doing, we're going to use some return-oriented programming. And what return-oriented programming is a technique attackers use to exploit a program by reusing small pieces of already existing executable code instead of injecting new malicious code. Because of this reuse of legitimate code fragments, ROP bypasses many defenses designed to stop code injection, such as marking parts of memory as non-executable. Now, if you want to get into bypassing DEP and ASLR and all that fun stuff, I'm also doing a course on that at both B-Sides Ottawa, B-Sides London, but both those are going to be at Malware Village itself. So I will be covering that stuff. So now we got to put these bad characters in. So let's do that. Okay, we're good. So let's 6 troon bad carrot up high. Okay. 6 troon bad. And it worked. Okay. So now what I'm going to do is I'm going to keep stepping over until we get back 2, 3, 4. So we're at BO5. Let's have a look at. Okay, we're at that one. So 1, 2, 3, 4 more steps. So I'm just going to step ahead 4 more calls. And we're at DO5. Let's have a look at DO5. Okay, so we're at the Malik call here now. Okay, so let's step forward to the mem set. Okay, so let's have a look here. We can go back and have a look at mem set. So here's the destination, and it's going to zero it out in the count. So let's have a look at Control C, and as you can see, there's that. So let's step to the next call. Let's have a look at that again. And as you can see, the zeros from the mem set zeroed out what was up here. Just some junk memory. Now, we are at D69. So let's step to the next one. D77. So we're down to the call here. So basically the string copy has already been called here. So let's have a look at that buffer. And I'm going to display this in bytes this time. Whoops. And as you can see, besides the first troon here, we got 1, 2, 3, 4, 5, 6, 7, 8, 9. And as you can see, we go right through all the characters and there's no other bad characters. So if there was another bad character, it would get to that bad character and then it would be nothing but zeros after. Because our payload would get truncated or stopped. So we have no bad characters. So that's bad character analysis. I think I have a sheet on bad character analysis. I feel I do. Yeah, I do. So bad character analysis, common the null byte 00 often terminates C strings. Okay, so runners up to that, we got the new line X0A, as well as the which is a carriage return, and we have 0D, which is a form carriage return 0D and form feed FF. Bad characters can be buffer dependent. Sometimes you'll have one buffer, like it will get copied into initial buffer, and then into the second one, it will have different bad characters. So you have to check all your buffers. Some buffers only allow alphanumeric. Like it's very strange once you get inside this thing. We will inject all our characters into the buffer to determine what caused our exploit to fail. And as you can see, we have no bad characters except for null bytes. So that's the bad character analysis done. So we're getting close to taking this fucking thing over. So let's get going here. This is fun. I'm so glad I put this together. It is actually a lot of fun to play with. And I hope you guys enjoy it as well. So let's attach to a process. Vuln server. receive and hit go. So let's go back to our Kali. So we just did our bad character analysis. We found out that um, only 00 was a bad character. So now we got to move into um, building out our exploit. So now I need a jump ESP gadget. So what a gadget is a little piece of code within now if you're bypassing dep or whatever, it has to be in the text section, but this right here, we can get any of our gadgets from pretty much the whole binary because it isn't um filled with hold on one sec here. Let's start that over again. Let's attach our debugger. Okay, so now I'm gonna have to look for a few things here. So the first thing I'm gonna do is open up my NASM shell. So NASM shell is just part of Kali Linux. So open up NASM shell here, and I need a jump ESP gadget. So what this will do, it'll tell me the opcode. So FFE4 is a jump ESP gadget. So now what I'll do is there's a little way to figure this out right inside our WinDebug. So let's have a look at the loaded modules. And as you can see, there's a whole bunch of different modules here that I can get gadgets from. If we look at this one right here, what do you guys see right away? Should see these zeros right here at the beginning, which is going to truncate and cause problems. So we can't use Vuln server at all because it has null bytes to start with. So what we're probably going to do is this S function right here. So I'm going to copy the start and end here. And what we're going to do, whoops, is we're going to do a search for the bytes FF and E4, which is our jump ESP gadgets. So let's have a look through that binary for these. Oh, whoops, I put the wrong, it didn't copyright. Hold on. Control C. Let's get. Okay, so as you can see, we have a whole bunch of different jump ESP gadgets we can use. So let me just copy this one. Let's have a look just to make sure. Actually, we'll unpack it. And as you can see, yep, it's FFE4 jump ESP. So I'm going to copy this gadget and we come back over to our Kali Linux and we place our gadget in backwards. Now, I put this up here just so you can see. I put it in little endian backwards. So here's the address here. Here's how it's placed. So the last goes in first. That's little endian convention. You can also use the struct import pack and just put it in normally. So whatever preference you have, you can use both here inside of Python. So struct and import pack is a pretty cool feature we can use. So now what I'm going to do, I'm going to send this exploit. I'm going to put a breakpoint on our gadget. So let's copy. Jesus, had a stroke there or something. What's happening? Okay, so I'm going to set breakpoint at jump ESP just to make sure our jump ESP does take. So let me just set the receive hook. And this is just to make sure our jump ESP works right. Sometimes it might fuck up. So let's have a look. Okay, so we're sending 8 Troon exploits. Okay. Okay. And we hit our breakpoint. I'm going to hit go again. We really don't need to worry too much about this. I just want to make sure my jump ESP gadget is in the right place and it's getting triggered. Perfect. So as you can see right now, we have our jump ESP gadget, which is this one right here. And as you can see, it's the same. So the jump ESP gadget's being taken, and it's jumping to 9C8. So we can see ESP here is pointing towards 9C8. So let's have a look at what ESP is pointing to. And it's pointing to our threes. So now what I need to do, I know the jump is going to be taken. It's going to crash here, of course, because it's going to go to threes, which is like nothing, right? It's so it'll crash. So what I'm going to do, I'm going to put some NOPS, which is no operation X90, and this gives it a bit of padding. If you don't put the NOPS in, most of the time it's not going to work. So I'm going to put some NOPS in, and then I'm going to put my shellcode in. We're going to do basic vanilla buffer overflow and take over this server. So fun stuff. So that's that. Um, what are we doing? Okay, so we know our jump ESP gadget works. Let's fire up the vulnerable server again. Okay, so we have our vulnerable server set up. I'm going to set the same breakpoints. Um, let's see. Okay, so next we're going to move on to 10. So I've already made my shellcode here, and I've placed my shellcode um, just above my payload run here. So basically what's going to happen, the Troon and the dot are all there. Our 2006 A's are there. Our jump ESP gadget will jump to 90s, which are NOPs, no operation. So it'll just, this is called a NOP slide. So it'll hit the no operation, flow through 10 of those really quick, and then hit our shellcode, execute it, and call home. So what I'm going to have to do now is set up my listener. Fun stuff. Okay, so let's set up my listener. Okay, so we're all set up here. So we're far away, and this is some kind of Russian server. We're going to try to take it out. Now, this takes a second. We're listening, of course, on the port that's open, our IP address, and we have a reverse TCP handler set up. So we're listening. Okay, so next we're going to send this shell, and we'll see what happens. Okay, so 10.py. 3. Okay, 10.py. And off it goes. And I didn't start my I didn't start my my WinDGB, but that happens. Let's come here and grab the jump ESP gadget, and we will set up our debugger to breakpoint on that, and then set our breakpoint on the receive side as well. Good. And now we'll run it, which we forgot. And if we hit go here, we hit our jump ESP. So let's have a look at. So as you can see now, our stack pointer is pointing to our NOPs right up to here, and then BB7B. So let's go back. Let's have a look at our shell code. BB7B. So it's going through the NOPs, and then it's hitting BB. Oops. Edit. Undo. Okay. So this should jump into our shell code. Fingers crossed here. Everyone crossed their fingers with me. Okay, so let's hit go. And go. And let's go back. Let's have a look at our listener. Now it started to reverse TCP handler, but then it got truncated. Okay, so I think that's probably to do with my breakpoints I had put in. So let's finish it off here. Let's open the phone server, attach process. This time we're not going to put in any breakpoints. We're just going to let it run. And we hit go. And let's hit yeah, so it was not valid and closed. So I'm going to have to open up another interpreter listener here. Wonderful. Okay, so we have our reverse TCP handler. Debugger is running. So let's run 10 again. Let's run 10. And as you can see, a whole bunch of system stuff has popped up here. So that's usually a good sign. And as you can see, we have full interpreter control, full interpreter shell over this server. We're in Newfoundland, Canada, the server's in Russia, and now we have full control. So I hope you enjoyed this little intro to reverse engineering. What I hope everyone takes away from it is just some of the tools and some of the processes, and even just some of the language. And what you would need, of course, is assembly. And I'm putting out a course on assembly in the new year, so stay tuned for that. So I hope you guys enjoyed. Take care, and I'll see you guys in London and Ottawa. Okay, bye.